Hello, chemistry students. If you're watching this video, it means you've already watched the video on determining empirical formulas and molecular formulas. If you have not watched those videos, please do so first. This video is going to continue on those topics. However, it's going to be a little more difficult because it's based on combustion analysis and using data from actual experiments to calculate empirical and molecular formula. So it's not as simple as you being given the actual data. It's kind of analyzing it and using mole ratios to calculate it. So because this is a combustion analysis, combustion is a type of reaction. So we're first going to kind of preview reactions in general. The reason why it's so important to view chemical reactions in chemistry is they help power things around us every day. So they help move our cars, they provide electricity. And basically, when bonds are broken and new bonds are formed and atoms are rearranged, there are differences in potential energies held in those bonds that causes changes in energy, right? Because energy cannot be created or destroyed, it can merely be transformed. So changes in potential energy result in releasing maybe in kinetic energy or some other form of energy such as light and heat. So one of the simplest of all reactions is a combustion reaction. In fact, when we discuss reactions, the first reaction I talk about are combustions. So why are combustion reactions the simplest? Typically, there is a fuel source, okay? So there is a fuel source, and the fuel source is burned, and we require oxygen to support combustion. That's why if you want to put out a fire, you can throw a blanket over it. Or if you have a fire in a pan, you can put a lid on it. Without oxygen, combustion will not occur. And then typically if we're dealing with the organics, the products are going to be carbon dioxide and water. So the reason why combustion reactions are the easiest reactions is 3 of the 4 parts of it are the same. One reactant is always oxygen. The 2 products are always carbon dioxide and water. So what can change? Well, obviously the ratios and the balancing of the equation can change, and the fuel source can change. So I said the fuel source is organic, so I could have even written it out as C, H, and even O, because glucose, which is C6H12O6, is an example of a combustion. It's internal, but it is combustion. And I can put X, Y, and Z because the fuel sources, carbon, hydrogen, and oxygen mole ratios can differ. What will not differ is it requires oxygen and it'll produce CO2 and H2O. So we burn methane, right? And we do that, for example, in the lab, we use methane, which is a fossil fuel, in our Bunsen burners to boil sometimes water so that we can have a hot bath. And when we consume and burn this organic compound that has a ratio of carbon to hydrogen of 1 to 4, so those variables X and Y would be 1 to 4 mole ratios, we combine it with oxygen and we produce CO2 and H2O. So one of the things that you really need to understand is that when you have a combustion reaction, all of the carbon from your fuel source, so the carbon is this black ball right here represented, all of the carbon goes into the CO2. So if I know the mass of the CO2, I can know the initial mass of carbon because I can't create or destroy matter. If I look at my fuel source, the white balls are the hydrogen. All of the hydrogen is converted into the H2O. So if I know the mass of my H2O, I'll know the mass of my hydrogen. Now, why is that useful? Well, if I know the mass of my hydrogen and I know the mass of my carbon, I can convert that to moles, get mole ratios, and determine the mole ratio of the organic compound that I initially started. So by weighing the products of CO2 and water, I can determine the molecular formula for the fuel source that I start with in combustion analysis. So, combustion analysis is a common technique. We burn a fuel source and then we weigh the amounts of products produced. So generally, when we're talking about this, we're using organics and again, carbon, hydrogen, and sometimes also oxygen. All of the original form of carbon is converted to CO2, the hydrogen to H2O. If there is also oxygen in the fuel source, we'll have to subtract the masses of carbon and hydrogen from the original mass of the fuel source to get the mass of oxygen. And then from the mass of oxygen, convert that to moles to get the mole ratio. So once all the masses of the elements are determined, we can use those masses, convert them to moles, get mole ratios, and get the beautiful empirical formula that we discussed in the earlier videos. So this is basically your combustion analysis. You burn a fuel source, you absorb the water, you weigh the water out, you get the mass of the water. If you have the mass of the water, then I can get the mass of the hydrogen because the hydrogen comes from the fuel source. Then you can absorb the CO2, weigh out the mass of the CO2, and then once you have the mass of the CO2, you can get the grams of the carbon because again, the carbon is from the fuel source, okay? So here's a challenging problem. I have the combustion of some fuel. Now this particular example, we only have carbon and hydrogen, okay? And it produces 1.83 grams of CO2 and 0.901 grams of H2O. What's the empirical formula? So I'm looking for the X and Y. I'm looking for the mole ratios of carbon to hydrogen. Now, how can I do that? Well, what I could do is I can say, well, if I have 1.83 grams of CO2, I should be able to get grams of carbon, right? Because percent composition, and get moles of carbon. Just like if there's 0.901 grams of water, I can get the moles of water and convert that to moles of hydrogen because it's a 2-to-1 mole ratio. So let's take a look. So the first thing, I convert the grams of CO2 into moles of CO2. And how do I do that? Well, there's molar mass. There's 44.01 grams of CO2 per 1 mole, giving me moles of CO2. And then I do the same thing with hydrogen. Convert the grams of hydrogen that was absorbed in the combustion analysis using its molar mass and get the moles of H2O. So awesome, we have moles of CO2 and moles of H2O. Now what? Now we convert the moles of CO2 to moles of just carbon, right? Because we don't really care about this oxygen's mass, okay? Because we're looking just for the mass of only the carbon and hydrogen to get the mole ratios, or the mole ratios rather. So in the moles of CO2, I know there's 1 mole of CO2 and 1 mole of carbon. So that gives me the number of moles of just carbon. Now with the moles of water, I know in 1 mole, there's actually 2 moles of hydrogen. And I know that because of that subscript 2 there. But what this does is from converting the grams of CO2 to moles of CO2 and moles of carbon and converting the grams of H2O to moles of H2O and now moles of H, I can use that as mole ratios. And as in the earlier videos, what do we do for mole ratios? We pick the smaller mole ratio and divide it into, oh, whoops, I circled the wrong one, look at that. We pick the smaller mole ratio and we divide it into both. So the smaller mole ratio is 0.0416 moles of carbon. I divided it into both and I end up getting for carbon 1, but unfortunately for hydrogen, I get a mole ratio of 2.4. So when I look at 2.4, I see that that's not an integer. So how can I make 2.4 an integer? I have to figure out what do I need to multiply 2.4, and whatever I do for 2.4, I have to do to 1 to get that to be an integer. So really, you just want to focus on the 0.4, right? So 0.4 is what? 4/10? And we can simplify 4/10, can't we? We can. So we can simplify 4/10 to 2/5. And when I look at this denominator of 5, that's what I want to multiply both these numbers by so that I get an integer. So I want to multiply both of these by 5. And when I do that, when I multiply 1 by 5, I get 5. And when I multiply 2.4 by 5, I get, whoop, that's a typo, I get 12. Now the reason why, and if you see there was a typo right there, if I had multiplied it by 10, right, because I could have just swung that decimal over, I would see that if I multiplied this, I would have got C10 H24, but the simplest mole ratio is what the empirical formula is, and both 10 and 24 can be divided by 2 to give me the C5H12. And that would be my simplest empirical formula, my simplest answer. Sorry about the typo there. So that would be that example. Now, if you did multiply by 10, because maybe you didn't like, doing what I showed you here with the 4/10, 2/5 multiplied by 5, that's okay. You could have done that, right? You could have multiplied this by 10, but just remember, when you get the C10 H24, that's not the simplest ratio. 2 goes in both of that, and then you can just finish it off right there if you prefer to do that. That's totally fine. But now let's actually do a harder example. Let's do one where we actually have to incorporate in the unknown, there's oxygen. So the problem reads, upon the combustion of 0.8233 grams of a fuel source that has carbon, hydrogen, and oxygen, and it produces this amount of carbon dioxide and water, find the empirical formula. So we have to remember, okay, that we need to convert not just to moles of carbon from the grams of CO2 and not just the moles of hydrogen from grams of H2O. We're going to actually have to take that all the way to grams because this sample, right, some of it's carbon, some of it's hydrogen, but we need to figure out what mass, how many grams of oxygen, so that we can subtract that. So all of the carbon goes to the CO2, which we have as 2.445 grams of CO2. All of the hydrogen goes to H2O, 0.6003. So we need to convert those masses to masses of just those elements. So the first thing, convert 2.445 grams of CO2 to moles of CO2, and then convert the 0.6003 grams of H2O into moles of H2O. We did that earlier. And then, just like before, we convert the moles of CO2 to moles of carbon. And again, it still has that 1-to-1 mole ratio. And we convert the moles of H2O to moles of hydrogen, and that still has the 2-to-1 mole ratio. So we're good. We know the moles of carbon, we know the moles of hydrogen, but we still need to get Z. We need to get the moles of oxygen. This is where it's a little trickier. We have to go a little further. We have to convert the moles of carbon and the moles of hydrogen all the way to grams, because once we have the grams of those, remember this original mass, 0.8233 grams of this fuel source, once I have the grams of carbon and the grams of hydrogen, I can subtract the grams of carbon and subtract the grams of hydrogen, and be left with grams of oxygen, which I can then convert to moles to get that mole ratio. So I need to get the original mass of oxygen. How am I going to do that? Subtraction. So I take the mass of carbon. How do I do that? I take the moles that I've derived. This is the same thing I did earlier, but now I'm taking it a step further. I'm converting the moles to grams. So now I know the grams is that. So really, I can come over here and subtract 0.6673 grams of carbon. And then from the moles of hydrogen, right, I can use its molar mass and figure out the grams of hydrogen. So now I'm going to subtract, 0.06715. And I'm going to subtract these numbers from the original amount, and I'm going to get what remains is the grams of my oxygen, which is 0.0889 grams of oxygen. Now again, to get X, Y, and Z, it is not a gram ratio. It is a mole ratio. So what do I do with the grams of oxygen after I subtracted it to get it? Now I need to convert the grams of oxygen to moles. And I do that using molar mass. So now I have the moles of oxygen. So now all the moles of oxygen, I have the moles of oxygen, I have the moles of carbon, and I have the moles of hydrogen. I can now go back to my mole ratios. So I have all the moles. I pick the smallest number and divide every single one by the smallest number. The smallest number was the moles of oxygen. So I divide all of the numbers by the moles of oxygen, and I end up getting a ratio of 10 to 12 to 1. And because these are all integers, I don't need to multiply it by any number like I did in the previous problem. So I'm done. I can just keep this as my final answer, and that would be the empirical formula for this fuel source. Now, I only started with 0.8233 grams of it, but I'm looking for the empirical formula. I'm looking for the mole ratio. That's X, Y, and Z, and that's what I found with the combustion analysis and determining the empirical formula. So this is, I know these are tricky problems, but if you watch the first video on empirical formula, and then you watch the second on molecular formula, and you watch this slowly and pause and then rewind it, it will make sense. So thank you so much for tuning in. And yeah, if you have any questions, leave them. Thanks.